Welcome, everyone. Today we are exploring a paradigm shift in cybersecurity. With frontier AI models autonomously finding zero-day vulnerabilities, the bottleneck has shifted from tool capability to orchestration intelligence. We will learn how VCAO uses advanced game theory and mathematics to systematically thwart these strategic AI attackers. Let's get started. Let's introduce our core concept, VCAO, or Verifier-Centered Agentic Orchestration. Recently, frontier AI models have demonstrated the ability to autonomously identify thousands of zero-day vulnerabilities across major operating systems. This creates a paradigm shift. The bottleneck in cybersecurity is no longer tool capability, it is orchestration intelligence. Traditional workflows rely on ad hoc heuristics to decide where to run a fuzzer or a static analyzer. But against a highly strategic, AI-driven attacker, heuristics fail. VCAO solves this by formulating OS vulnerability discovery as a rigorous, repeated Bayesian Stackelberg search game. A large reasoning model acts as the orchestrator, deciding exactly where to look, which tool to use, and how much compute budget to allocate. By transitioning from reactive guessing to mathematically optimal resource allocation, VCAO fundamentally minimizes the expected damage an attacker can inflict. Let's look at this flowchart to visualize the paradigm shift. The emergence of the frontier AI threat has caused a security bottleneck shift. In the past, the bottleneck was tool capability, which led us to rely on ad hoc heuristics, ultimately resulting in a suboptimal defense. Today, the bottleneck is orchestration intelligence. We must manage our defensive compute wisely. This leads us to VCAO and game theory, which provides a mathematically optimal allocation of our analysis tools. VCAO guarantees we are spending our defensive budget in the exact locations that disrupt the attacker's best-laid plans. To understand VCAO, we must understand the underlying math, Bayesian Stackelberg security games. In game theory, a Stackelberg game involves a leader and a follower. In our context, the defender, the VCAO orchestrator, is the leader. We move first by committing to a mixed strategy, which is a randomized probability distribution of where we will deploy our analysis tools. The attacker is the follower. They observe our defensive posture and calculate their best response to maximize their damage. But why is it Bayesian? Because in the real world, we don't face just one type of attacker. We face APTs, insiders, and opportunistic scripts. The Bayesian formulation mathematically models this uncertainty across multiple attacker profiles. The deep dive realization here is commitment power. By moving first and committing to a defense, the defender mathematically guarantees a higher utility than if both sides moved simultaneously. We systematically channel the attacker toward less damaging paths. This state diagram maps the flow of a Stackelberg security game. It begins with the defender commits phase, where VCAO allocates its mixed strategy coverage. The sequence moves to attacker observes. The attacker analyzes our defense, triggering a Bayesian calculation that accounts for their specific capabilities and goals, whether they are an APT or an insider. Next, the attacker best responds, selecting the exploit path that offers them the highest expected payoff given our defenses. Finally, the payoff is evaluated. By anticipating this exact flow, VCAO computes the optimal initial commitment to minimize that final attacker payoff. To play the game, we need a game board. In VCAO, this is the intra-kernel attack graph. What is this? It's a directed acyclic graph that mathematically maps the operating system's entire attack surface. The graph is defined as G equals V, E, C, phi, psi. The vertices, V, represent the building blocks of the OS, entry points like syscalls, internal functions, privilege boundaries, and ultimate attacker goals like root access. The edges, E, represent how data and control flow between these nodes. Why do we need this? Because the VCAO orchestrator requires a quantitative map to calculate exactly how an attacker might chain vulnerabilities together. In our deep dive, we assign a prior probability, phi, to every node based on historical defect density and CVSS scores. By multiplying the probabilities along the edges, VCAO calculates the exact statistical likelihood that an attacker can successfully traverse a specific path to compromise the system. Let's walk through this attack graph architecture. An attack begins on the left at an entry node, like a syscall or iactl. The attacker attempts to move to an internal logic function. The dotted line labeled phi represents the mathematical prior probability that a vulnerability exists here. From the internal function, the attacker hits a privilege boundary. The transition depends on psi, the probability that the edge is exploitable. If the bypass succeeds, they reach the critical red node, the attacker goal, achieving root or exfiltration. VCAO analyzes millions of these interconnected paths simultaneously. Now we arrive at the heavy mathematical lifting, DBSSVD. This stands for Decomposed Optimal Bayesian Stackelberg Solver for Vulnerability Discovery. We format our game theory into a mixed integer linear program, or MILP. This is a class of mathematical optimization that allows us to find the absolute best defensive strategy under strict resource constraints. Let's look at the math context. We want to maximize our expected utility, factoring in the probability of different attacker types, PL. We are constrained by our total compute budget, B, which must cover the cost, W, of analyzing various files, C. How does MILP handle the enemy's logic? It uses a clever mathematical trick called Big M linearization. This allows us to encode the attacker's if-then best response behavior as linear constraints. The deep dive here is that the solver simultaneously calculates our optimal coverage vector while anticipating the exact path the attacker will pivot to, ensuring our limited budget is spent with maximum disruptive impact. This flowchart shows the inputs and outputs of the DOBS-VDM-LP solver. We feed three critical variables into the solver: our total compute budget, B, the probabilities of various attacker types, PL, and the massive attack graph, G. The optimization engine processes these matrices. Crucially, it applies Big M linearization to mathematically enforce the attacker's best response constraints. The final output, the green node at the bottom, is the optimal coverage vector, C. This vector is our exact mathematical battle plan, dictating precisely where to assign our AI agents. Let's discuss the verifier in verifier-centered agentic orchestration, the Bayesian belief update. Once our MILP solver tells us where to look, we deploy external tools like CodeQL for static analysis or syscaller for fuzzing. However, these tools are noisy. Static analysis generates massive false positives, while fuzzing often misses deep logic flaws. How do we trust them? We mathematically merge their noisy signals into a single, unified truth probability using Bayes' theorem. When a tool finishes, it returns an observation, an alert, a crash, or clean execution. We calculate the new belief state, BT plus 1, by taking our prior belief, BT, and multiplying it by the conditional probability of the observation given a true vulnerability. The deep dive is that VCAO knows the specific true positive and false positive rates of every tool. If a fuzzer generates a crash, the mathematical belief of a severe vulnerability spikes instantly. If CodeQL generates a warning, the belief rises proportionally to CodeQL's historical accuracy. The game board is dynamically redrawn. This cycle diagram illustrates the continuous Bayesian belief update loop. We begin on the left with our prior belief. We execute a tool, like a memory sanitizer, which yields an observation state. If it's an alert or crash, we follow the top path for a high likelihood update. If it's clean or times out, we follow the bottom path for a low likelihood update. Both paths feed into the Bayesian formula application node. This math generates the posterior belief, which then feeds backward to become the new prior belief for the next round of the Stackelberg game. How do we build this math into a working system? We use the 6-layer VCAO architecture. This is the complete software stack that operationalizes our theory. Layer 1 is the surface mapper, an AI agent that extracts all syscalls and parsers. Layer 2 is the attack graph builder, mapping the control flow dependencies. Layer 3 is the brain, the game theoretic ranker running our DBSSVD solver. Layer 4 houses the parallel executor agents. Here, independent AI agents concurrently run dynamic fuzzing, CodeQL, and memory sanitizers across the targets designated by Layer 3. Next, we have Layer 5, the cascaded verifier, and Layer 6, the safety governor. Our deep dive focuses on Layer 5. It acts as a Swiss cheese defense model to filter out the noise. It forces every finding through a strict 3-stage check: reproducibility confirmation, severity assessment, and deduplication. This cascading logic dramatically reduces the false positive rate before any human engineer is alerted, saving massive amounts of labor. Here we see the 6-layer VCAO architecture visualized as a vertical stack. Data is pulled from the bottom up. L1, the surface mapper, feeds raw code topology into L2, the attack graph. This data enters L3, the game theoretic ranker, highlighted here because it's the mathematical core of the operation. L3 pushes execution orders up to L4, the parallel executor agents. The results are pushed up to L5, the cascaded verifier, for strict filtering, before finally hitting L6, the safety governor, which ensures the AI remains isolated and heavily audited. It is a seamless loop of discovery and verification. Let's apply this to a real-time, highly critical use case, defending the Linux kernel. In a massive evaluation, VCAO was deployed across 5 major Linux kernel subsystems, tasked with replaying 847 historical CVEs and scanning live upstream code. The scenario tested VCAO against a simulated strategic AI attacker. The VCAO advantage became immediately clear. Standard coverage-guided fuzzing runs somewhat blindly, hoping to hit a crash. VCAO, however, used game theory to actively direct syscaller to complex networking code where crashes are likely, while specifically assigning code QL to authorization paths where logic bugs hide. The results were staggering. VCAO discovered 2.7 times more validated vulnerabilities per unit of compute budget than standard fuzzing alone. Let's deep dive into why VCAO outperformed even non-game theoretic AI agents because it mathematically understands diminishing returns. As one kernel subsystem became exhausted, VCAO dynamically reallocated GPU hours to fresh targets. Furthermore, the cascaded verification reduced the false positive rate reaching human reviewers by an incredible 68%. This chart illustrates the performance multiplier of VCAO. We measure severity-weighted validated findings per unit budget, or SVB. At the top, the fuzz-only baseline scores a low 0.42. The static-only baseline achieves 0.59. Moving to AI, a multi-agent system without game theory hits 0.81. But VCAO, utilizing rigorous Stackelberg game theory, dominates the field with a score of 1.13. It is vastly more efficient, proving that throwing uncoordinated AI at a problem is insufficient. Mathematical orchestration is the ultimate force multiplier. To conclude, we must look at the mathematical guarantee of VCAO's future success, sublinear regret bounds. What does this mean? In online Stackelberg learning, we achieve a regret bound of big O of the square root of t. In basic terms, t is the number of rounds played. As time goes on, the systems regret its performance penalty for not knowing the attacker's strategy perfectly on day 1 shrinks dramatically. This matters immensely because we rarely know the exact profile of a zero-day AI attacker immediately. Using advanced algorithms like Thompson sampling over Bayesian beliefs, the math guarantees that VCAO will rapidly converge on the optimal defensive posture. To survive the coming era of AI-driven cyber warfare, advanced orchestration and game-theoretic mathematics are mandatory. Mere tooling is obsolete. To master these cutting-edge cybersecurity concepts and future-proof your career, I invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final mind map summarizes the VCAO era. At the core, we have integrated game theory, specifically Stackelberg games and the Dobbs VDM LP solver. This powers our agentic orchestration, driving parallel executors with Bayesian beliefs. Crucially, the system boasts guaranteed learning through sublinear regret models and Thompson sampling. All of this culminates in real-world defense, securing critical infrastructure like the Linux kernel while drastically reducing human fatigue through false positive reduction. The math is our ultimate shield.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available like Microsoft. You can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials and click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our portal.